graduate award. And then he joined, to my luck, OSU and my research group, and he received his PhD about a year ago, and now is working at McGill University in Canada across the border. He has done very nice work on developing 3+1 dimensional hydrodynamics for collisions at the beam energy scan, where you have to keep track of the dynamics of baryon number and baryon diffusion. And it's not just a hydrodynamic code, but a full model code with pre-hydrodynamic stages and post-hydrodynamic hadronization, just like the codes that we have at higher energies, but now also able to discuss issues like the critical point in the phase diagram, at the subject of his talk today. And I welcome you to give this talk. Lipei, go ahead.
Yeah, thanks a lot, Li, for introducing me. Also thank the organizers for inviting me. Today I'll be talking about hydrodynamics near the QCD critical point. So this talk will be mainly in 3 parts. In the first part, I will talk about bulk dynamics of nuclear collisions at low beam energies. Discuss off-equilibrium dynamics of hydrodynamic fluctuations. And finally, I will talk about the feedback of hydrodynamic fluctuations on bulk dynamics. Let me start with some motivation for the studies covered in this talk by showing you this QCD phase diagram as a function of temperature and the baryon chemical potential. We know at low temperature, quarks and gluons are confined in hydrons. So we have this hydron gas phase. At higher temperature, we can have the confined quark-gluon plasma phase. We can also talk about the phase transition between those 2 phases. At low chemical potential, people can do first principle lattice calculations, which show that this phase transition is a rapid and smooth crossover. There are also models of QCD, which show that there might be a first order phase transition between those 2 phases. So along this line, you can have a mixed phase of these 2 phases. And then when you move towards this crossover, you end up at a second order phase transition, which is also called the critical point. We don't know where this critical point is exactly, because we cannot do first principle calculations in this region. Experimentally, we can carry out heavy ion collisions at different beam energies from high to low beam energies. And the idea is when you lower the beam energy, then we can probe higher chemical potential regions in the QCD phase diagram. Indeed, if you look at this repeated density of net protons, you can see that near midrapidity, when we lower the beam energy, the net proton yields increases, which indicate a higher chemical potential. There are different heavy ion collision facilities ongoing and in plan, and they are carrying heavy ion collisions at different beam energies, especially the beam energy scan program at RHIC was designed for doing this energy scan. Beam energy scan has been finished, and the data is under analysis. So the idea is, if we can measure different observables and then plot them as a function of beam energy, if at some beam energy the system can pass near the critical point, then we may be able to see some signatures at some beam energies. Here I'm going to show you 2 examples of such measurements at beam energy scan program. This is the directed flows slope at near midrapidity as function of beam energy for those identified. So here, these blue dots are for the pions. You can see the slope is negative, and then the magnitude increases when we lower the beam energy. On the other hand, we can see for protons, it is very interesting. First, the slope is negative, and then it goes to positive. And it seems to be there is a minimum somewhere near 20 GeV. Early on, people thought this might be related to the first order phase transition, but I also should mention that there are studies which can reproduce a minimum without a first order phase transition. So our understanding is really also evolving. This is the measurement of a ratio between the fourth order cumulant and second order cumulant for net protons and protons as function of beam energy. People are measuring these high order cumulants because they are believed to be very sensitive to the enhancement in the correlation length. Misha Stefanov found that for example, the fourth order cumulant, also called kurtosis, should have a non-monotonic behavior as function of chemical potential, or in some sense equivalent to beam energy. He also found that, so with the map from 3D AC model to QCD, he found that this kurtosis should have a dip compared to the baseline value at a lower chemical potential region or high beam energy. And there will be an enhancement at even lower beam energy. So here we can take a look at these measurements, and you can indeed see some kind of suppression compared to the baseline value. There is a suppression at higher beam energies, and then there seems to be some enhancement at even lower beam energy. But unfortunately, currently we have large error bars, so we cannot tell. Hopefully after the beam energy scan and two analysis get done, we can see a clear signature. However, I should also mention that whether there will be a dip depends on the choice of parameters as shown by this study. So this dip might disappear with some parameters. On the other hand, we can also see the calculation from hadron resonance gas with canonical ensemble with no criticality can also get this suppression relative to the baseline. So this measurement at these higher beam energies doesn't necessarily mean we are seeing some consistent with universality. But maybe at lower beam energy, if we can see an enhancement, that maybe means something, because this enhancement is believed to be very robust based on this study.
But what do you do with the very low energy points, the 3 GeV and I guess 2.5 GeV points?
What do you mean? What?
Well, the ones which are the ones which are in the far left, the 2 points on the far left, which go at 0 and -1.
Okay, so I mean, right now there are calculations from EuroQMD, which is a hydrogen gas model. So they seem to be consistent. So maybe that means we didn't really produce a quark-gluon plasma at all. So there is no really phase transition.
So there's no problem with having C4 over C2, which is negative?
I mean, this is maybe there is no phase transition at all, so I'm not sure. Yeah. Okay, I should also mention that all these expectations are from the assumption that the critical fluctuations are at the equilibrium. And later we will see that off-equilibrium dynamics can be important in fluctuation dynamics. I should mention that there are also other observables which are proposed in the last few years. For example, the ratio of light nuclei yields, which may be sensitive to the criticality. Of course, these new observables would be very helpful, because if we can finally find different observables which are sensitive to criticality, and we see signatures near the same beam energy, that will really mean something, right? Here, let's take a further look at this, how to calculate high order cumulants from multiplicity distribution of net protons. Here I'm showing the raw measurements of from star at different beam energies of net proton distribution for central lead-lead collisions at midrapidity. So at different beam energies, the mean value, the mean value is corresponding to the mean yields at midrapidity at different beam energies here. So of course, different models should be able to reproduce this mean value as a basic requirement. On the other hand, we know the high order cumulants, including skewness and kudoses, they describe how the distribution deviates from Gaussian distribution. As I said, those high order cumulants are sensitive to the enhancement in correlation length. So that means near the critical point, these some distributions will be strongly deviate from Gaussian distribution. I should also mention that there are multiple effects which can influence high order cumulants, which may not be from criticality. For example, you change the momentum cuts, you can change the values you obtain for high order cumulants, and there can be contributions from initial volume fluctuation, the diffusion in hydronic stage. So that means, I mean, ideally we should try to remove those contributions that are not from critical point from the final measured high order cumulants. Also, that means when we do theoretical calculations of those high order cumulants, we should make apples to apples comparison. All right, let's say one day after we get a lot of data and the different observables, and we believe that we find some signatures in different observables, and we believe that is from critical point at some beam energy. We still need to map a point in phase diagram from this beam energy. That is certainly not trivial either. You may have seen this version of phase diagram. So you can see here at different beam energies, they have some well-defined trajectories, but certainly this is just a sketch. We have different methods to map this beam energy to points in phase diagram. For example, the statistical thermal model, which have been proven to be very successful at LHC energies. People are also working towards beam energy scan energies. We also see this plot a lot. You can see people use the yield measurement at different beam energies at mid-rapidity to extract a temperature and the chemical potential on the Friezau surface, assuming grand canonic ensemble. So in that sense, we can get some mapping between beam energy and a point in the phase diagram. Also, we can use lattice QCD, which can calculate susceptibilities on lattice, and which can be compared to the measured multiplicity cumulants. But we know that the measurements has some momentum cuts, but on the other hand, lattice doesn't really have such cuts. So in some sense, they are not really directly comparable. These two methods assume the produced systems are at the thermal equilibrium. However, we know that in heavy-ion collisions, we can produce really dynamical systems, and the viscous effects can be essential. To take into account these effects, we can also use multistage dynamic model to do this mapping. In that case, then the location of the critical point and the phase boundary will be input from through equation of state. Such multistage framework should it be able to describe the bulk dynamics of nuclear collisions. Here we focus on low beam energies. They are related to the mean yields mainly. So this the reason that we need a multi-stage description is because heavy-ion collisions really go through several different stages. At top break energy and even higher beam energies, the Lorentz contraction is really strong before the collision. Then you can think that all these collisions happen at the same time. So in this case, the boost invariance is a very good approximation, and we can focus on the transverse deposition of energy density and then give that to a hydrodynamic evolution. At the particleization, then we need to convert hydrodynamic fields into particles, and then we give these particles to some hadronic description, such as U or KMD, which can do rescattering. And finally, we arrive at some stable particles, and then we can use them to calculate the observables, which can be compared to experimental measurements. However, at lower beam energies, you can see at this beam energy, the Lorentz contraction is much weaker. You can imagine that those nucleon collision pairs will happen at a different time and a location. And the boost invariance will not be a good approximation at those low beam energies. So that means we need to update our multi-stage framework. For example, in the initial stage, we need to construct some dynamic initialization for hydrodynamics. In this hydro stage, we need to include the evolution of conserved charges, including baryon charge, electric charge, and strangeness. Also, that means for the equation of state and transport coefficients, we need to get their dependence on those multiple chemical potentials. If you want to study the critical point, then you also need to include some singularities in them. At the particleization, of course, we also need to include those non-zero chemical potentials. It also makes difference whether you want to assume grand canonical ensemble for each fluid cell, or you want to apply some conservation laws in some regions on the hypersurface. If you propagate high order if you want to propagate your fluctuation dynamics, then we also need to translate fluctuations into correlated particles, which is also very tricky. So with such, at this point, people are making progress in different directions, but we still don't have a comprehensive multi-stage description. Here, on this slide, I want to emphasize how important it is to have rapidity dependent measurements to constrain those multi-stage frameworks at low beam energies. Here, I'm showing you the calculation of net proton distribution at different beam energies for different centrality classes from two calculations from two models developed by Chenshen and collaborators. Let's focus on the central collisions here. These data points at mid-rapidity are from the measurements of star. So if we focus on mid-rapidity, you can see we cannot really tell which model is doing better because both of them fit the measurements pretty well at mid-rapidity. Fortunately, we have measurements covering larger rapidity window from BRAMS, and then with them we can tell this model seems to be more off from the measurements. So here the point is that we really need rapidity dependent measurements so that we can constrain multi-stage framework at low beam energies. Currently, the beam energy scan program is completed at the fixed target energies. People are measuring more data points at different rapidities, but for those higher beam energies, hopefully we can also get more data points if you can cut the repeated coverage into a few more bins, that will be more helpful to constrain those models. To show you even more how we can use the rapidity dependent measurement to constrain our models, here I'm showing you an example of using rapidity dependent directed flow. Here we use a multi-stage framework with parameterized initial conditions. And then we try to fit the pseudo-rapidity density of charged particles and the rapidity density of net proton distributions at these 4 beam energies. At those 2 high beam energies, actually we only have those the net proton distribution for those 2 high beam energies. For those 2 low beam energies, we took measurements from lead-lead collisions at 2 nearby beam energies, and then do some scaling to constrain our model. This is for central collisions. And then we use the model to calculate V1 distribution for those identified particles at 4 beam energies for the intermediate central collisions. Here, let's focus on the V1 of baryons. So at high beam energies, because we have less baryons, so we have worse statistics at those beam energies. That's why you see large wiggles. Let's focus on the V1 of protons and lambdas at 19.6 GeV. So you can see, very interestingly, we can see the distribution of lambda has an S-shaped distribution. And you can see that our model can reproduce this behavior. So by reproducing this behavior, we can constrain our model. So how did we achieve this? We can go back to the collision.
Just briefly, you say 19.6, but the data are from 17 GeV. Did you scale the data to 19?
No. So these solid squares are from 19.6 GeV by star, but these open symbols are from this measurement.
Oh, okay, thank you.
Yeah. All right, let's go back to the beginning before the collision. So this is the illustration of 2 colliding nuclei in XZ plane. They're about to impact. This is the overlap region. Here you can see these nucleons will go through less collision compared to the nucleons here, because of the difference in the thickness of the other nucleus. So that means these nucleons will end up with less rapidity loss. So with that, we can construct an initial distribution for baryons in the reaction plane like this. So here you can see the baryons here will be at a forward space-time rapidity, but here it will be a bit behind. Overall, this peak has this slightly shifted structure. So after the transverse expansion builds up with this imbalance distribution in baryon density and the transverse expansion, we can see that the baryon here will be flowing in the positive x direction. Here, baryons will be flowing in the negative x direction. Correspondingly, you can have positive V1 here, but negative V1 here. So you can see here how we can use this rapidity dependent measurement to constrain the model. Here, let's take a further look at this longitudinal evolution of baryons, because this is very important in low beam energies. Let me show you this final net proton distribution again. As I said, near mid rapidity, when we lower the beam energy, the net proton yields increases. On the other hand, the rapidity dependence is also very interesting. So at the higher beam energy, you can see 2 peaks, and then when the beam energy is lower, those 2 peaks get closer, and then finally they merge into a single peak. So this is the so-called the baryon stopping, and the baryon stopping is stronger at the lower beam energies. let's focus on those blue dots first. We can see that since these net protons have these two peaks, that means on the free side surface, we can expect the chemical potential also have two peaks. So as function of rapidity. So that means for the initial stage, before hydro starts, we should also have some double hump structure in the baryon density as a function of space-time rapidity. That means in the initial stage, we already have some baryon stopping, and we can call this initial baryon stopping before hydro starts. And then we can turn on the hydrodynamic evolution. For the baryon evolution, the viscous effect is the so-called baryon diffusion current, and it transports more baryons from a high chemical potential region to low chemical potential regions like this. So overall, this lumpiness will be smoother compared to the case without baryon diffusion. Finally, you can see this baryon stopping is in space-time rapidity, but we finally, what we measured is this baryon stopping in the momentum rapidity. At low beam energies, because we don't have booster invariance, and this mapping is not also non-trivial. So the final baryon stopping is a combined effect from the initial baryon stopping and hydrodynamic transport. So in those in those multi-stage framework, we should try to disentangle these two effects. There are some studies using charge balance functions to extract the baryon diffusion. But as far as I know, these studies are done for LHC energies where the authors assumed booster invariance. So if we want to use this method for lower beam energies, we still have the same issue here that we don't have a well-constrained model. The baryon stopping is important also because the fluctuations in baryon stopping will also contribute to high order cumulants. Also, it will affect how the system evolves in the phase diagram. Here we already see that along rapidity or space-time rapidity, we can see the system has some non-trivial distributions in baryon density. So that means at different rapidity, the system will probe different regions of the phase diagram. Let me show you this. Here we focus on longitudinal evolution. So we look at 1 plus 1D evolution without a transverse expansion first. This is some phase diagram trajectories corresponding to different space-time rapidities. And you can see here let's first focus on those starting points of those trajectories. When we move from midrapidity to forward rapidity, we can see first these starting points move to a larger chemical potential region and then turns around to low chemical potential region. This is directly related to this distribution. As I said, when we move from midrapidity to forward rapidity, the baryon density first increases and then decreases. That explains this turning. And now when we have hydro evolution, those trajectories look like this, follow those dashed lines. In some sense, those curves are parallel to each other. So you can see indeed those trajectories are going through different regions with the phase diagram. So here, the critical point and the critical region are just for illustration purpose. So you can see that those they may get affected by the critical point in different ways at different rapidities. This is very similar to the beam energy scan program where we focus on midrapidity but at different beam energies. Here we focus on one single beam energy but at different rapidities. This motivated people to study this rapidity scans idea besides energy scan. All right, now let's look at the effects from some viscous effects. First, we turn on the baryon diffusion, and you can see those trajectories get modified in different ways. For example, at these locations, those trajectories move to higher chemical potential region. Here, the trajectory is moved to lower chemical potential region. Overall, they are getting closer to each other. And this is the direct effect from the transport of baryon charge caused by baryon diffusion current. As I said, baryon charge goes to lower chemical potential regions because of the baryon diffusion current. On the other hand, of course, this is also the consequence of the conservation of baryon charge. Okay, we also studied the effects from shear stress tensor and bulk viscous pressure on those trajectories in our CPOT proceedings. You can see similarly, those trajectories are moved to higher temperature region simply because of viscous heating. But the effects from bulk viscosity is smaller. It only happens near the end of the evolution because bulk viscosity is parameterized to have a peak near the phase transition temperature, which is near the end of the evolution. So here, I think we can clearly see that because at low beam energies we don't have boost invariance, the longitudinal dynamics couples different rapidities within the same fireball. So even if we want to focus on midrapidity, we should also keep in mind that it will be affected by the other rapidities. All right, these results are obtained for 1+1D evolution, and then we can also try to see what happens in a 3+1D evolution with transverse expansion. Here, I will show 3 different locations within the fireball in the transverse plane, okay, from center to the edge of the fireball. And this is what we got in a 3+1D evolution. If you look at each plot separately, you can see these trajectories are modified compared to the ideal case in a similar way as in the 1+1D case. But the difference is that when you move from the center to the edge of the fireball, because the initial temperature is lower, so they might scan different regions of the fireball. Okay, so we only look at one beam energy, but you can imagine that if you want to pick out this trajectory at midrapidity and then combine these midrapidity trajectories with other beam energies, you can also imagine that the viscous effects will modify those trajectories, so they will be different from the ideal evolution, which is also always shown in the phase diagram trajectories. So at beam energy scan energy, we should always keep in mind the longitudinal dynamics.
Brief clarifying question: what root S is this plot?
Sorry.
Which root S did you choose for this plot?
Oh, this is 19.6 GeV.
20 GeV. Okay.
Okay, now let's switch to the off-equilibrium dynamics of hydrodynamic fluctuations. So there are different approaches to fluctuation dynamics. Here I'm just taking this nice summary from Thomas Jeffers' talk a few weeks ago. The studies in this talk is based on the HydroPlus framework, but in some sense it can be derived from the hydrokinetic approach. So in that sense, they're equivalent to each other. Let's take a closer look at those equations. So here, psi can be understood as fluctuation of a hydrodynamic variable, which such as energy density or flow velocity. Here, this is the equal time to correlation of this fluctuation. As you can see, they happen at the same time, but different locations. And then we do a Wegener transform. You get a mode with a wave number k. So this mode is continuous with continuous wave numbers. So we can say modes with different wave numbers. People have derived the equations motion of those modes, which is same here. So this part is the time derivative in the co-moving frame, and this is the equilibrium value of this mode, and this is the off-equilibrium value. So the dynamic value of this mode relaxes to its equilibrium value, and the relaxation and time scale is controlled by this relaxation rate. And then we can apply those equations to a specific mode. And here we first look at the slowest mode in heavy ion collisions, and it is the fluctuation of entropy per baryon. And similarly, this is the two-point correlation, and then we can do Wigner transform, and then we get a set of modes with different wave numbers Q. In the hydrodynamic limit, one can calculate the equilibrium value, which is given by heat capacity over baryon density squared. In the critical regime, this heat capacity is critically enhanced, and this equilibrium value with different wave numbers is given by this expression. This is the critical scaling of heat capacity. This part gives wave number dependence. This expression looks complicated, but simply speaking, the equilibrium value of slow modes with different wave numbers is determined by the local thermodynamic properties of the background fluid. So that means when the background fluid evolves, the equilibrium values are also evolving with it. Then we can study the off-equilibrium fluctuation dynamics using the equations I have shown you 2 slides ago. And first, let's propagate those fluctuations on top of transversely expanding fluid with with longitudinal boost invariance. Let's say this hot fireball has a temperature higher than critical temperature near the center of the fireball, and let's say on this dashed circle, the temperature is at critical temperature. So that means the correlation length peaks on this circle, and then it expands. It expands and cools down. So the temperature at a critical temperature, the circle at a critical temperature shrinks to a smaller radial distance. On the other hand, because of the transverse expansion, the fluid cells which were at critical temperature now moves to a larger radial distance. So keep this in mind, and then we propagate those fluctuation modes on top of this fluid. Here I'm showing you the movements of 2 modes with 2 different wave numbers in the radial direction. And this is the equilibrium value. This is the non-equilibrium value. And the different colors means different times. Here you can see for the equilibrium value, this critical peak is moving inwards. That is explained by the shrinking of this critical circle. And on the other hand, the non-equilibrium values show interestingly different behavior for those 2 modes. First, you can see for the small q mode, this critical peak is moving outwards. So that means this mode is not really relaxing to its equilibrium value, but instead it is carried out by the outgoing flow. This is the so-called advection, and this moving outwards peak is explained by this white dashed line here. Okay. On the other hand, the large Q mode, you can see the critical peak is moving inward, but the value is somewhat smaller than the equilibrium value. So that means this mode is relaxing to its equilibrium value to some extent, but not fully equilibrated. So what caused the difference between those 2 modes? We can take a look at this relaxation equation again. As I said, the equilibrium value is evolving together with the background fluid like this. And the relaxation is controlled by the relaxation rate. The relaxation rate is proportional to wave number squared. So that means for small Q mode, the relaxation rate is small. So it cannot really relax. Instead, it is carried outwards by the outgoing flow. On the other hand, the large Q mode has larger relaxation rate, and so that it can equilibrate to some extent. Let's briefly summarize. We can see that we have seen there are two effects at play in the off-equilibrium fluctuation dynamics. First is the advection, which is caused by the outgoing flow. And the second is the relaxation, which is controlled by the relaxation rate. So advection dominates in the dynamics of small Q mode, and the relaxation dominates in the dynamics of large Q mode. So for different wave numbers, these two effects competing with each other. Here with these small modes we are talking about are corresponding to two-point correlations. So they are about the Gaussian fluctuations. If we do freeze out, and then we get variance of multiplicities, which are not really sensitive to the critical point. So if you want to calculate high order cumulants, then you have to propagate those non-Gaussian fluctuations, which are corresponding to a 3-point and 4-point correlations. There are some recent development in this direction as well. So then I want to make some connection from this off-equilibrium dynamics to something that can be measured. Is rapidity dependent cumulants, which were proposed by those authors. So let me show you this plot again. The idea is near mid-rapidity, you can see at different beam energies, the chemical potential on the freeze-out surface should have some non-trivial distributions as a function of rapidity at different beam energies. So that means the system freezes out at different locations in the phase diagram on the as a function of rapidity. So based on this idea, you can see this is the phase diagram, you can see here we have three symbols which are corresponding to mid rapidity and somewhere away from mid rapidity. For the second row, this is simply a shift in the mid rapidity chemical potential. The authors then calculated the fourth order cumulants, the kurtosis, in two ways. First, they calculated the kurtosis for the entire rapidity range. So here you can change the rapidity coverage, you get different values. On the other hand, they calculated the kurtosis for a few bins. In other words, they cut the rapidity coverage in a few bins and then calculate kurtosis separately. And they found in this way, you can see, for example, in this case, you can see a peak within the rapidity coverage. So the idea is that if we can measure the cumulants within a few rapidity bins, then we can probe the phase diagram specifically. We can probe the finer structure in the phase diagram. But I should point it out that this study is based on the assumption that the critical fluctuations are in thermal equilibrium. Okay, so what else can we learn from this study? So you can see here, since we are using the same rapidity coverage for different beam energies, but on the other hand, we do see different structures in the chemical potential as function of rapidity at different beam energies. So if we only measure the cumulants for a single rapidity beam by averaging out all the using all the particles within the rapidity coverage. That means we are averaging out or smearing out different structures in the chemical potential as function of rapidity at different beam energies. On the other hand, if we can really measure the mean yields and high order cumulants at different rapidities, in that case we may constrain the equation of state, and we can study the off-equilibrium fluctuation dynamics along rapidity direction. As I just described, the advection will also play a role in the longitudinal direction because of the longitudinal flow. All right, finally, let's switch the final topic, the feedback of hydrodynamic fluctuations on both. Discuss the slowest mode in heavy ion collisions, whose relaxation rate scales with correlation line like this. But in fact, there are other modes. So their relaxation rate scaled with different powers of psi. So that means when we get closer to the critical point, when the correlation length increases, the relaxation rates of those modes are suppressed in different ways. For example, this mode will be, the relaxation of this mode will be suppressed most strongly, and then this one. So the system goes to the critical point, those modes will go off equilibrium one by one. In this framework, they found the slowest mode is the diffusive mode, given by this expression. We have discussed this. Of course, there will be also a next to slowest mode, which is shear mode. This is a vector, and its relaxation rate is given by this expression. There can be other modes, of course. So these fluctuations can have feedback on the equation of state and transport coefficients. For example, the shear mode can contribute to baryon diffusion. You can see it has a fluctuation of flow velocity and the baryon density. So it's not hard to imagine it can contribute to the baryon diffusion. First, let's study the off-equilibrium correction to entropy density from the scalar mode. So the idea is, since we introduced those additional degrees freedom, the entropy density of the system will be modified. So the HydroPlus framework gives this expression to calculate the entropy correction from these modes. From this expression, you can see whenever one mode is away from its equilibrium value, then it can contribute to this entropy density. Large Q mode can relax to their equilibrium value, and then they will make no contribution to entropy density. And the contribution of small Q modes will be suppressed by this Q squared factor. So that means the dominant contribution to this entropy density will be from the modes with wave numbers near this characteristic wave number. And this wave number should make the relaxation rate approximately the same as the expansion rate. Then this delta S can be estimated by this characteristic wave number cubed, and this equilibrium entropy density is proportional to temperature cubed. So in this way, we can qualitatively estimate the contribution, and it was found to be tiny. And then we also did the calculation quantitatively, and indeed it found to be very, very small. On the other hand, in an earlier study, the authors used a different relaxation rate. But they also calculated the off equilibrium correction to the radial flow, and you can see the correction is below 1% from those off equilibrium modes. And then we want to study the off equilibrium contribution to.
Sorry, you said it's different. How was it different? How did they get this different conclusion?
What is different?
You said they.
Okay, so the relaxation rate is different. You can see here, our relaxation has this Q-squared dependence, but here, this study, the relaxation rate goes to constant value.
Okay, thank you.
Okay, so here we want to study the critical effects in the baryon transport. First, we need to isolate all the critical contributions in the baryon dynamics. To do this, we write this relaxation equation for baryon diffusion. Okay, this is the dynamic value. This is its Navier-Stokes limit. It relaxes to the Navier-Stokes limit, and the time scale is controlled by the relaxation time here. First, we rewrite this gradient into two terms so that we can isolate the criticality in isothermal susceptibility chi and the baryon diffusion coefficient. And then we need to find the critical scaling in the relaxation time of baryon diffusion. As we just discussed, the slowest mode contributing to a mu is the shear mode, this vector mode, and near the critical point, the framework gives the relaxation rate. It scales with correlation length like this. So near the critical point, this mode relaxes slowly. So the relaxation time of baryon diffusion will be dominated by this critical mode. Okay, so that means the relaxation time of baryon diffusion has the same critical scaling at this mode, which is given by cosine to the second order. So then we can put all these critical effects in the baryon dynamics. Here, to see the critical effects, we put a critical point here, and then we parameterize the correlation length so that when the system enters this critical region, correlation length grows. And then we do the dynamics with critical effects. Here I'm showing the trajectories at different space-time rapidities, and then we'll compare to the case without critical point. These trajectories with no critical effects were shown a few slides ago already. And then we see that all these trajectories are on top of each other. So that means we didn't see any critical effects on baryon transport. But on the other hand, we do see enhancement in the correlation length. But why did this happen? So first, we see that the enhancement in the correlation length only happens near the end of the evolution when the system enters the critical region. And on the other hand, we found that the baryon diffusion already decays to very small values at the early stage of the evolution. So that means when the system enters the critical region, the diffusion is really small already. And even if we get some critical effects, when it enters the critical region, nothing happens. So that's why we didn't see any difference here. All right, on this slide, there are some detailed discussions about why the baryon diffusion decays fast. You can take a look at this later. I will skip this slide. Okay, now I can go to the summary. Here in the first section of the talk, I demonstrate that the rapidity-dependent observables are really essential for constraining dynamic models. And at low beam energies, because we don't have boost invariance, the longitudinal dynamics couples different rapidities within the same fireball. And in the second part of the talk, I discussed the off-equilibrium dynamics of fluctuations. And we have seen two effects at play in off-equilibrium dynamics. First is the advection, and then it's the relaxation. In the last part of the talk, I discussed the back reaction on the bulk evolution from the off-equilibrium scalar mode, and it is found to be negligible. And then we studied critical effects on baryon diffusion from a vector mode, and the effects are found to be negligible as well because the baryon diffusion decays to a very small value very quickly before the system enters the critical region. And that's it. Thank you very much for your attention.
Thank you very much, Lipei. This was whirls through a lot of complex dynamics. And there is quite a few questions already in the chat. I will start by going through these questions and calling the commentators to ask them out loudly. And while that's going on, people can raise their hands if they have additional questions. So let me go through the chat and go back to the beginning. I think Stefan was the first to comment. I leave it up to you, Stefan, in which order you want to ask your questions.
Okay. Yeah, sorry, I got plenty of questions. So the first one is more of a comment where you were in your introductory slides, you were discussing sort of like, the dynamics of, how V1 behaves as a function of beam energy and so on. And what you showed in those slides, for example, yes, it's the middle slide. I mean, the middle figure of slide 2 is your QMD as a baseline. And
right.
that, and towards lower root S, that becomes very questionable, since we know from lots of studies at the Beverluck and at GSI that potential interactions between nucleons play a major role, in particular when it comes to the behavior of V1. And your QMD in its standard form, which is being used by the community, does not have those potentials. So flow-related or observables that are sensitive to the equation of state will be described very poorly by your QMD if you go into an energy range that's fixed target energies of 2 to 5, 6 GeV per nucleon, or root S around 3 or 4. And so that's a word of caution to the entire community, right? Don't use this as a baseline and say you have discovered interesting physics because your QMD fails. That's absolutely not the case. I mean, there is very well-known physics there that has been actually done well by other older transports that could focus on the dynamics of the nucleon force at low beam energies. So that was just a comment, right?
And your comment would also apply if your QMT happens to agree with the data. Yes,
sure. I mean, it's for in this domain where the nucleon interaction plays a major role. I wouldn't trust your QMD. It's perhaps fine for particle production, pions and kaons, but yeah, be aware that these potentials are missing in that calculation, and that may play a major role.
Okay,
then
for your comments. Moving
on to slide 4, and actually in the course of your talk, you've already sort of shown that that's something that has to be treated with caution. Many years ago, Hannah and subsequently Chun did a great visualization of a hydroevolution in a TMU plane, where they visualized really every single cell in the hydro as it goes through the TMU plane. And what you find is that it's a diffuse cloud, which is pretty broad, that wafts through that phase diagram. Yeah, so it's not a trajectory. And so the question is, what are the implications for you discussed mapping of root S to TMU? Does that mapping even make sense? Yes, is a precise mapping even possible if you think about what a broad range of T and mu values are being probed in a single hydro event at a single beam energy that goes to that plane.
Yeah, but I think your comments is about the multistage framework, dynamic framework, right?
Yes.
So I think in that case, the location of the critical point and the phase boundary would be some input through equational state, right? So if our model finally works well for all different kinds of measurements at different beam energies, that means the input of the location of the critical point and the phase boundary is correct, and in that sense we can constrain where the location of the critical point. I think.
No, I don't think you understood my question correctly. Yes.
Okay.
Even if you take a single hydro shot of an event by event hydro, yes, you will cover a broad range of T and mu values, right? So,
yes.
So only very few cells of that hydro evolution will actually even come within the vicinity of the critical point. And I think that is a major, major challenge, right? Even if your hydro works perfectly well and you have the perfect implementation of a critical point with all its phenomena, are you bringing actually enough matter into the vicinity of the critical point to get a signal?
Yeah, indeed.
Yes, I think that's the challenge. Yeah. And so I caution everybody, you know, these trajectories look great, and then you can study them as a function of beam energy or rapidity. But the reality is that the realistic hydro calculation will have a gazillion of these trajectories all in one event. And then the question is, you know, are you going to be sensitive because you're not getting that much matter into it?
But if I may jump in here, didn't you show, Lipei, that part of that broad spread of these blobs in Hannah's and Chun's simulation comes from the fact that you are including all rapidities at the same time? And your point was, by looking at rapidities differentially, you can try to separate this a little bit. It's not a sharp separation because of the effects that you mentioned, in particular thermal smearing, but there is some additional information by doing this rapidity differential. I mean, in the end, Stefan's point is of course well taken. Only some trajectories in the entire fireball get close to the critical point, and many don't, and that needs to be folded into the final interpretation of the data. But you can focus your attention on trajectories that you expect to get closer to the critical point, and see whether you see something there.
Suggestion: why don't you do then that Chun visualization with a cut-on rapidity to see how it looks?
Oh, okay. Yeah.
Yes, I think that would be a much more honest way of visualizing what happens. Yeah. Okay, sorry for monopolizing the discussion.
Yeah, Stefan, can I ask you to postpone your third question until we have taken somebody else, and then we'll return back to you? Okay, Arima Kusei has a question.
Oh yeah. Could you please turn to the slide 10?
This one?
Yeah. Here you showed that the diffusion effect of baryon charge among all these rapidity slides. So just curious why the phase trajectory of this seems so special.
So I think this is because this space-time rapidity is near the high chemical potential region. So
okay.
If you have diffusion, then the baryon charge will be transported away from here. So that's why it goes to lower chemical potential region when we have diffusion.
Okay, so this means that the diffusion effect is quite strong at this pseudo rapidity.
Yes.
Okay, I see. Thank you very much.
Yeah, sure, no problem.
Thank you. I don't see any hands up. So, and I think the next question and the last question on the chat is again from Stefan. So, Stefan, you have another
All right,
chance.
sorry about that. I apologize. So, slide number 8. You made a statement that baryon stopping is stronger at low beam energy, and I'm not so sure about that. I would like to get some clarification there. And here's my thinking. So this goes back to perhaps the 1980s and 1990s, where phenomenologically it was found that in a proton-proton, but also in heavy ion collisions, every nucleon-nucleon interaction, at least initially, makes the nucleons lose 1 unit of rapidity. Now that of course means that if you're at high beam energies, yes, you're still going to be far away from midrapidity, and that's why this characteristic dip kind of stays there. But if you're at low beam energies where your entire rapidity gap is less than 4 in total units, moving the nucleon by 1 unit towards midrapidity means that they're going to pile up at midrapidity, just like what you see. But that doesn't mean that stopping has been stronger. I mean, the rapidity loss per nucleon is still just 1 unit of rapidity. It's just that you're kinematically, constrained in your overall rapidity range, and that's why you see the pileup.
Yeah. So I think
evidence that stopping is stronger at the low energies, meaning that you're losing more rapidity per nucleon-nucleon collision.
So I think a better way to qualify this is to calculate the overall rapidity of baryons, and then compare to their own incoming beam rapidity. That is a better qualification about the baryon stopping.
I think, yeah, that would be an analysis that sort of tries to address the question I posed, right?
Right. But, and I think what Lipei mostly wanted to say is that the effect of baryon stopping on the baryon distribution is strongest at mid rapidity when you go to lowest energies. But that happens even for constant energy independent baryon stopping strength.
Oh, absolutely. I was just cautioning people about the word it's strong.
So I have a few hands up now. Let's stay at Duke for the moment. Bernd?
Yeah, hi. Actually, I'm at Yale right now.
But
that's fine. So I have a question on slide 9. And my question is whether this effect that for higher rapidities or pseudo rapidities, the effective chemical potential shrinks again. Is that actually supported by data, or is it just simulation?
You mean this part, the tail?
Yeah.
Yeah, I mean, I'm talking about the left plot where eta equal 1.75 and 2 actually are, I mean, at 2 you're getting very small chemical potential. Is that based on chemical analysis from data, or is it theoretical?
Well, I mean, from theoretical calculations, if you want to, I mean, we don't really have data at
sure you
rapidity.
do. Sure you do, because we have fixed target experiments.
Okay. So at least for this beam energy, so there's we try to fit this tail. Okay, we just extrapolate it to be very small values in the net proton yields at a large rapidity, and then you do theoretical simulations, right? And
yeah, so in other words,
tail,
you don't have data there.
No.
It would be really interesting to talk with the experimental collaborations, because they have fixed target data now, of course, from 7.7 GeV down.
Yeah,
so they can cover the
and
entire.
So it should be possible to actually confirm or refute that.
Right. We eagerly waiting for that analysis. Yeah.
Okay. At least I think from the preliminary results, I don't see really this tail. I don't remember I have seen that.
Yeah, they
I
may
mean,
not have. They may not yet have done the analysis.
I think so. I think they haven't shown the analysis yet. I think they are in the process of doing that, but they are still working on that. That's what Nu told me. Was that it, Bernd?
Yeah, that was it.
Yes. Yi, you have a comment.
I think I have a question, and thank you so much, Lipei, for the presentation.
Thanks.
So I think my question is general, and maybe not only for you, but also for the audience. So my question is, what is the predefined criteria? If I borrow the terminology used for the CME search, so what is the predefined criteria in your mind for the location of the critical point?
Notation, you mean?
What is the predefined criteria if I borrow the terminology they use for the CME search? Yeah, so what is the does such criteria even exist? Or if it exists, what is that? What in your mind?
Well, I'm not sure if we really have any such signals purely from universality arguments. I don't really think so. At this point, I think we really need to consider the dynamics and do calculations at different beam energies. Yeah.
Maybe another way of saying it is that in order to develop such criteria, you have to know better than we do now which of these non-monotonic behaviors that have been proposed are actually robust under the inclusion of full dynamical evolution. And that program has not yet concluded. That we're still working on that. Anybody else wants to comment on that? Xiaofeng, is your comment related to this, or is it something different?
Something different. I have a question, actually.
Yeah, let's just see whether there are any additional comments to the question by Yi-Yin. Doesn't look that way, so Xiaofeng, why don't you switch topics?
Okay, thank you. Yeah, hi, Lipei. Could you go to the slide 14?
Let's see that. Yeah, here.
Yes, actually, the star has. We are analyzing the PS2 data. Actually, we are trying to taking this proposal from this paper to study this finer tuning of the rapidity, trying to looking for the possible critical signal here. So, but that's in great. This proposal that actually is moving the rapidity center away and on the 2 blocks of the rapidity range. So I'm wondering whether this rapidity gap in between will have some will suppress the possible signal if we leave a gap there.
I'm not sure I understand. Can you say more about that gap?
Yeah, actually, the way that the method that proposed in this paper is to actually define 2 blocks of the rapidity, which is symmetry around the center of the rapidity, and move it away from the midrapidity towards the backward or forward rapidity. Then certainly we'll leave a gap in between these two blocks rapidity. And that gap, actually, I'm wondering whether this gap will cause suppression of the signal. Yes.
Sorry, I don't understand what that gap.
Okay, maybe.
Yes, Yin, do you understand the question? Can you answer it?
I'm not sure, but my suggestion maybe is for Lipei is I think this our calculation is still illustrative. If one can do more realistic estimations, and I think that would be nice. And I think the effect that Xiaofeng mentioned presumably is built in. If there's such effect, and with more realistic situations, we should be convinced whether those qualitative features is robust or not.
Yeah.
Yeah, it would be nice that you can carry out a similar simulation in your hydro calculation and demonstrate whether there are some effect. Yeah.
So Xiaofeng, you are saying you are working on such an analysis. Do you have some idea when we can expect some results?
No, actually, we are analyzing the BS2 data with this method you propose in this paper to see the rapidity dependence. Yeah.
What is the beam energy you're gonna analyze for this?
BS2 actually 19 GeV. Yes.
For one beam energy or all the beam energies?
Well, we are trying to working on this one energy first, then we'll move to other energies. Yes.
You think if you do this rapidity band cumulants, you have good statistics to see those rays and down those structures?
We have enough statistics, yes, but we're trying to seek help from maybe theorists to whether this gap will cause some other effect beyond this. I mean, so for example, we'll suppress some short range or long range correlation if you leave a gap there.
I think this is very nice that this analysis can be done, and you should not look to the theorists too much at this point. Just do the analysis, and while they are working on it, I think it's good to do this analysis without prejudice.
Yeah. I think these repetitive band observables would be much more helpful than one single data point.
Carry out a more differential measurement.
Yeah. That's great.
And
good to know.
Maybe another question is that we also have measured this 3 GeV fluctuation, and also the wide rapidity coverage proton DNDY at 3 GeV. So I'm wondering whether you can perform similar simulation as using your hydro code, the 3 GeV.
Yeah, I'm not sure if hydro is applicable for that beam management though.
Yes, it's really a challenge. But
also because the hydro code are usually in the Milnor coordinates, but for that beam energy, we really need to go to Cartesian coordinates. Yeah.
Okay. Thank you. Yeah.
Thanks.
I think at this point, I do not see any additional questions. And if that is the case, then I will just take this opportunity to thank again Lipei for your nice talk.
Thank you very much. Thanks.
And I'll hand back to the organizers, the other organizers. Xiaofeng, any announcement, or will we just close the meeting?
Oh, thank you, Lipei, for this very nice presentation, and thank you everyone for joining. And I think this is the end of this seminar. Yeah, thank you. Bye-bye.
Okay.
Bye-bye.
Thank you.
Thank you.
Bye.